Lecture 8.2, Magnetic Domains and Creating Magnetic Fields. We know that a bar magnet has two poles. If we break a magnet in half to isolate the north from the south pole, can we do this? And the answer is no. This creates two smaller magnets. So the question is that if we continue breaking these magnets into smaller and smaller pieces, what do we find? So in other words, I imagine that I have two magnets. Excuse me, I have one magnet. And now what I'm going to do here is I'm going to break it in the middle. So that I have the south and the north. And now when I break it, I end up with smaller magnets. But what I find here is that I create two mu magnets. And then if I continue to break one, right? If I continue to break this, and if I do this again, you're going to find that I'm going to get smaller magnets. But they still each have a north and a south pole. So if I continue this process and I go all the way to the atomic scale, what do I find? At the atomic scale, we find a rotating and spinning electron. And conclude this is the cause of magnetism. The electron's motion is described quantum mechanically. And is well beyond the scope of this course. I will present a rough analogy that should not be taken seriously or too seriously, but just enough to give some insight. I hope that made sense. So I'm going to start with the analogy that many people give. So we want to look at what is the motion of the electron. So the analogy that I'm going to give is I'm going to talk about Earth rotating and spinning around the sun. And so what we find here is that there are two separate motions. One of the motions is that, so if I think about the sun, let's say that this is the sun right here. And then what's happening here is that over here, I have our blue pale dot right here, which represents the Earth. And what we're seeing here is that this guy is rotating around the sun. And so what we're seeing here is that there's actually two motions. One motion here, which I'll call, let's say, this motion right here. This is what's called the orbital angular momentum. And this other piece is that you're going to find here is that the Earth spins on an axis about its own axis, and this here is called spin angular momentum. And what you find here is that we typically have notation that we write is that we say that the orbital angular momentum is typically given the symbol L, but I'm going to write orbit here. And the symbol that they typically give when an object spins about its axis is they use the symbol S, and this here is the spin angular momentum, but it's rotating. So what we find is that this whole system has a total angular momentum. So the system has a total angular momentum. And I'm going to use the language of quantum mechanics, and this is what it says, is that we have this angular momentum, which is called J, and it's a combination of the orbital angular momentum plus the spin angular momentum. And that's how we describe the motion of the Earth as it goes around the sun here. Now, we got to be really careful when I start to apply this to the electron's motion. But that's what I'm going to try to do. So I'm going to say that this analogy applies mildly to the electron's motion around a nucleus. Now, although the electron does orbit the nucleus, maybe I should write this down to be really clear. Although the electron does orbit the nucleus, and let me tell you, it doesn't do it in an ordinary way by any stretch of the imagination, but that's not the point here. The electron does not spin about its own axis. And let me tell you, yes, I'm well aware that there are courses and there's online that tell you that electrons do spin. They're going to tell you differently. But electrons do not spin. If electrons did spin, it violates two central principles. One, electrons are points, and have no surface. That immediately implies here is that points cannot spin about their axes. It's physically impossible. And two, if the electron did have a surface, that means it has some diameter, its surface would rotate faster than the speed of light. And that violates special relativity. Electrons do not spin. Unfortunately, they call this quantity spin. So this quantity goes by the name, or is called, intrinsic spin, because it has units of angular momentum. And it is a good choice. You know, it's a label and could have been called something else, like, I don't know, a toaster, a thingy, or whatever. Spin, intrinsic spin is a title. That's it. It doesn't have to do anything about it rotating about its axis. And I'll tell you that intrinsic spin is very abstract and definitely non-human. There's no way a human mind can come up with this. And it has, right? It has caused me numerous sleepless, how do you spell sleepless? Sleepless nights. Now, let's get back to the physics. So what do we know? The electrons total angular momentum is the cause of magnetism. Which has two parts. It has two parts. And so here's the way we write it down. What we say here is that we have a magnetic field. That's what causes it. And so what we need here is that in order to produce a magnetic field, we typically need numerous, right? So we need numerous what are called magnetic dipole moments. And when you look at this, it turns out that the magnetic dipole moment, that is proportional to the total angular momentum, which is then equal to the orbit part plus this intrinsic spin part. So if my numbers look correctly here, about 30% of the magnetic field is due to the orbital motion, and 70% is due to the intrinsic spin. So very similar to the Earth having two angular momentums, so do the electrons. So that being said, we could then come in here and say the following thing. In classical spin angular momentum, the electrons' motion is either clockwise or counterclockwise. Although this effective picture is wrong, it explains the language and somewhat the behavior of being magnetic. So here we go. So let's start to get to those pictures here. So since intrinsic spin is modeled, has angular momentum, classical spin is then going to be S, which will then be R cross P, which will then be R cross M times V, whose direction is derived by the right hand rule. So we're going to assume that the electron is a small sphere, which it's not. And now we're going to talk about the angular momentums here. So there are two possible rotations. So the first one is clockwise motion. Looks like this here. So I imagine that I have a sphere. And so here's my sphere. And because I have a sphere, that means it has a radius. It's an extended object. Now I imagine that if I'm going to have counterclockwise motion, then it turns out I have to come in and out like this. I got to rotate like this. So I'm saying that this is my momentum, which is looking like this. So now if I look at the right-hand rule, here's what it says. The right-hand rule says that if I have a vector r like this, and my momentum is coming out of the page like this, then the angular momentum in this case, my thumb is then going to point upwards, and it's going to have a spin vector pointing up like this. In other words, it rotates in the counterclockwise direction. In other words, this guy has a spin angular momentum pointing up. And by the way, if you take in chemistry, this is what's called spin up, because the angular momentum points up. That's why they call it spin up. Now, if I do the same thing with clockwise motion, so clockwise motion is just the opposite. So in this scenario, I also imagine that I have a sphere. So if I look at my radius here, this time the only way I can get motion that's going to be counterclockwise is that I have my momentum moving into the page, And in this situation, if I look at my cross product, I now have a vector like this, or I have this guy right here, which is P. And when I use the right-hand rule, that tells me that I now have a spin direction that points down. So in this situation, it now rotates in the clockwise direction. In other words, my momentum is pointing down, and therefore I keep putting the symbol for a vector, but that's my vector here. So when I look at this thing, I'm seeing a rotation that's rotating like this. Here, I'm seeing a rotation that rotates like that. So in this case, we call this spin down. Now I want to apply this to the electron. So if I apply this to the electron, so I'm going to apply this to a spinning electron, and you could see I put quotes because electrons don't spin. So then I see this scenario here. I have a sphere. And when I look at this sphere, it's going to be rotating. So when it rotates here, if it rotates like this, then we know that this is going to be in the counterclockwise direction. So therefore, I have a spin vector that tells me that it's pointing up. So what happens? This acts like a bar magnet. And so when I look at this guy, I really see this. The consequence here is that I have this guy right here. And yes, I am creating a spin that's looking, this guy is spinning like this here. And as a consequence, I get this dipole-like thing that looks like this. So this is the south end, this is the north end right here. And so as this spin, I can associate that this is the north, this is the south. And when I look at its magnetic field, I see that its magnetic field looks like a dipole magnet like that. So I would say that this guy right here is the intrinsic magnetic field of the electron. And the way we write this is that we come in here as we then draw it with an arrow. And this arrow tells us that this arrow, if it points up, it's north. That the tip is north, the tail is south. And so this right here is what we call the magnetic dipole moment. And this dipole moment is typically defined as the vector mu, and this means spin up. Now I can do the exact same thing if I'm going counterclockwise. So in other words, if I have a sphere here, so the big difference here is that now this guy is rotating in the opposite direction, clockwise. So if it's rotating in the opposite direction, in the clockwise direction, then this spin is going to be pointing down. So now we have a spin down. So this tells us that this guy is then going to operate like a bar magnet. It acts like a bar magnet. So in this situation, what we're seeing is that the dipole magnet behavior points downwards instead of upwards. So it reverses what we call the south and the north end. So then these field lines still come from the north and head up towards the south like this. Remember, it's superposition. So if I look at this thing, we now call this magnet, excuse me, we call this spin down. So because this is spin down, that means that the north, instead of pointing up, is now pointing down. And this has a magnetic moment as well. But we call this spin down. So when I think about a spinning electron, so a spinning electron produces its own dipole flavored magnetic field. So if I look at this thing, I'm saying that I'm going to have, if this is my electron right here, and let's say in this case it's spinning counterclockwise, I could have chosen the other one. That is the electron. So when I look at its magnetic field, I'm seeing that it's looking something like this. Now I just got to draw this symmetrically. And so I'm seeing here that I'm getting something like this here. And so when I look at the dipole moment of this guy, I'm seeing that this is what I mean by that dipole moment right there. So that means it has a north and it has a south end. So how do I get a magnetic field here? So if there are a number of magnetic moments, remember magnetic moments and magnetic dipole moments are exactly the same thing. If there are a number of magnetic moments, the magnetic strength of a material depends on the alignment. So let's say I have something like this. What if I have 4 magnetic dipole moments pointing like this? Then what you're going to see here is that in this case, I have more aligned magnetic moments. I'm going to have to move this a little over. And that tells me I'm going to have a strong magnetic field. But if I have this situation, where one of them is misaligned, what you're seeing then is that I have less aligned magnetic moments. So therefore, this is going to give me a weak magnetic field. And if I have no aligned dipoles, that means I have something like this, with the number of spins up versus the number of spins down, then that's going to tell me that I have zero magnetic field. So in simple language, a group of atoms like this are called magnetic domains. So a magnetic domain is a region where the magnetic field of a group of atoms are aligned in the same direction. In other words, I need individual magnetic moments to be magnetized as aligned with each other so that they point in the same direction. So what you're going to see here is that this is an image that I got from Wikipedia. And you could see here that each of these guys here is a domain right here. So here's another domain. So if I'm looking at this, this is a little region. And then I could have, by the way, they don't have to be smooth, but looks like this is another domain right here. So these are domains. So if I look at these domains here, let me see if I could copy just these guys. You could imagine that I have something like this. So if I look at this domain, maybe I have a magnetic field that points in that direction. So all of these moments are pointing like this. Maybe this domain points in a different direction. Let's say it goes in that direction. Or like this. So each of these guys is a domain where you have a group of atoms that have their magnetic moments aligned. So now we could answer the question, what do we mean by magnetism? The alignment of domains determines the strength of magnetization. So let's see if I can draw this nice and clean. So I imagine that I have a piece of material. And what I'm going to do here is that I imagine that I have little domains that sort of like I'm just drawing them randomly that look something like this here. So if I look at that, you could imagine that if I have a material like this, then I have to worry about whether I have random domains or not. So let me copy this and bring it over to here. So if I look at this guy, here's what I'm seeing. If I have random domains, then my arrows are going to point in random directions. So if I have random domains, then that tells me that the magnetic field must be zero. However, if the domains are aligned, and this would make it a very strong magnet or magnetic material, then if I have aligned domains, that tells me that the magnetic field is not zero. And in this case, this is what we would call a permanent magnet. All the domains are in the same direction. So now let's get to induced magnification. Induced magnetization. Now we could start to get to where we could start to talk about the physics. So I'm going to start with an analogy, and from electric polarization in chapter 1 of dielectrics, the permittivity value, epsilon, is a measure of the dipoleness of a material. In other words, it has the ability to recruit, dipoles. So we want to apply this idea to magnetic dipoles. So in a similar manner, what we're finding here is that here's a new constant. It's called the permeability, which is defined as mu is a measure of a material's tendency to align its magnetic moments. Just like the permittivity is a measure of its ability to align or create dipoles. when an external magnetic field is applied. If more spins are recruited to align, the higher its permeability value it has. So in this situation, if I have an external field, so you could imagine that I produce a field that's a north field pointing towards a south field. There's my magnetic field. Now, if I put a little dipole magnet in here, we know that there's two parts to this thing, and that the north repels the north and the south repels the south. And as a consequence, there is a torque that applies. So what I'm seeing here is that there's an applied torque, and that forces the magnetic moment to align. Now, once again, we need some external magnetic field to do this. So then, induced magnetization operates similar to electric polarization. In dielectrics. So if I look at this thing, I have a balloon. Let's say that I have a balloon right here, and this balloon has now been charged. So on one side, because it's a dielectric, the charges can't move, but that's my balloon nonetheless. I have a negative side. So over here, I have a neutral wall. So what you're seeing is that here I have a charged balloon, and here I have a neutral wall. If I bring this close enough, what happens? The balloon is now going to be close enough to the wall here where it produces dipoles. So then if I start to look at the atoms in the wall right here, what you're seeing is that the negative portion of the balloon creates a positive side to the wall, because now I build a positive surface charge. And in this situation, we then say that we've polarized the wall. The balloon polarizes the wall temporarily by recruiting dipoles. Induced magnetization does the exact same thing. So if I come over here and let me see if I can let me see if I can get one of these guys. So I have this. So now the thing that I want to do is bring a magnet. So if I bring a magnet close to this, what am I seeing? I have a magnet that I'm going to bring close to this. And right now I start with random alignments. But as I bring this thing closer, what happens? I induced magnetization on this material right here. And so what I'm really doing when I'm doing that is I'm doing this. I'm creating a stealth into this material. So this right here is now a south pole end. And on the other side, I get a north pole in here. I've induced this magnetization. So what I'd like to do is that I want to show you a video of a domain model that actually does this. So this is a YouTube video, and it's going to show a model, a domain model. So let's go look at that. So if I play this video, this is a simulation of a magnetic domain. So here's what you find. And you could see how the magnet causes induced magnetization on these compass needles. So once they settle, look what happens. They orient themselves into domains. I'm going to let you watch the rest of this video on your own, but that's what we're really looking at right there. So when I'm looking at those domains, that's what you want to pay attention to. Now, there's another video that I really want you to pay attention to, which is worth looking at. So if you were to go into the lecture link, there's one here that's called ferromagnetism. And that's a Wikipedia video that's worth looking at. So the magnetic domains is the one that we just looked at. This is the one that I'm not going to show, but it's on ferromagnetism, which is very well done. So if I go back to my screen, I want to remind you that you should go look at the, this is the wiki video on ferromagnetism. It's like 3 minutes long. Very well done. So what I'm saying here is that watch on your own.